screen shares, tak? Ekran jeszcze trzeba udostępnić, żeby widzieli.
Nie działa pomyśl, no.
Nie mogę touchpadem być może.
Aha, touchpadem. Nic nie działa.
Tak, to już działa.
Okay, please sit down. Let's start. So the last speaker of the conference is Aleksandra Kwiatkowska. Aleksandra is a junior professor at the University of Muenster and an associate professor at the University of Wrocław. She and also at Muenster, she's a member of a Center of Excellence Geometry. She's interested in descriptive set theory, dynamical topology, and Ramsey theory. She obtained her PhD in 2012 at Urbana-Champaign from Sławomir Solecki, and then habilitation in 2022 from the University of Wrocław. Okay, and now you are very welcome. Please, the floor and the Zoom are yours.
Thank you very much for this very nice invitation.
And now I need to go. Okay,
Works?
I think it should work because.
Great.
Yeah, works? Yes,
everything's perfect. Okay, so I will talk about, so here's a like, sort of short version of my title. So I will talk about Fraı theory, Ramsey theory, topological dynamics, and related topological groups. So here is a slight elaboration on what I want to discuss today. My goal is to present some of the work of Kehris Pestov-Todorczewicz. And what is it about? It is about connecting what's called structural Ramsey theorems. So I will start with that in a moment. And this connects with topological dynamics, with dynamics of corresponding topological groups. So I will also explain what do I mean by that. And we'll be interested in properties such as extreme amenability, which I will also define, minimal flows of particular topological groups, of automorphist groups of countable structures specifically. Okay, so I have to introduce some notions, some definitions. I'll try to give many examples. So first, let me start with something very simple. I want to talk about structural Ramsey theorems. And for that, let me recall classical Ramsey theorem. So here's a little bit of notation. So whenever I write n, I mean the set of natural numbers from 0 to n minus 1. So this is an element set of natural numbers. Now, for a set S, we can consider k element subsets of that set, where k is some natural number. And here is the notation that we will use, S over k. And then we can look at colorings of sets as well. So whenever I have some set X and I have some natural number R, I can color my X into R many colors. So R coloring or coloring is simply some function from X to R. Okay, and then, so this is kind of standard notation in combinatorics, this kind of arrow notation. And what does it mean? So here we have natural numbers R, K, M, and N. So R will be used for the number of colorings. We can think of K as small number, M middle size number, and N big number. So this notation, it stands for the following. So for any R coloring of k-element subsets of n, we can find a monochromatic set. So what do I mean by that? We can find an m-element set inside n, which we denote by S, which has the property that if we look only at those k-element subsets of n, which are entirely in S, then they all get the same color. So we can also say that S is monochromatic. Okay, so the classical Ramsey theorem from 1930 is the following. So whenever we have m, k, r, natural numbers, then we can find such a big N so that this Ramsey theorem holds. So in other words, yes, so we're coloring k-element subsets of n, and we can always find an element subset inside such that all k-element subsets of that get the same color. Okay, so this is the classical Ramsey theorem. And what I want to do now, I want to not only color natural numbers or subsets of natural numbers, but I want to color structures. So what do I mean by that? I want to color graphs, metric spaces, and various other objects. And I want to have analogs of that theorem. Okay, so when I say structure, what do I mean? So it's a structure in the sense of model theory, first order structure. So let's look at some examples. So examples of structures are, let's say, linear orders, graphs, linearly ordered graphs, metric spaces, partially ordered sets. So all these structures that I mentioned so far, these are relational structures. But we also have structures that involve functions such as vector spaces, group, etc., etc., etc. So here are a bunch of examples that you can keep in mind whenever I talk about structures. To be a little bit more formal, what do we have? We have a bunch of symbols. We have symbols for relations. These are those RIs. We have symbols for functions, FJs. Each of those symbols, they come with a natural number. So with some number mi for relations and some number fj for functions. So we allow 0 when we talk about function symbols. And then when I say a structure, I simply mean that I have a set with a bunch of relation symbols and function symbols interpreted. So here we have relation symbols are interpreted as subsets of some powers of A, and function symbols are interpreted as functions from some power of A to A. Okay, so everybody here that I listed can be realized in this way. Yeah, so for example, for linear orders, we have set together with a binary relation, which satisfies certain properties, properties of being a linear order. So same for linear order graphs, we have two binary relations, one for linear order and one for being an edge in a graph. In the case of metric spaces, so we can also code it as a structure. So we can say that like for every real number R, we can say that we can get a relation which says that those two elements are in the distance less than R. And simply, yeah, same with partially ordered sets. Yes, for let's say groups, we have also functions. We have, let's say, plus or times, and we have this trivial function which is used for 0.
Sorry, just
for the
a
distinguished
stupid
element.
question. You allow,
Okay,
here. So just a stupid question. You allow this n of I to be equal to 0, and this corresponds to constants.
Yes.
Okay, so you include constants in
Yes.
this
Yes.
in this setting. Okay.
Okay. So if you like, you can think more formally about structure. If you like, you can think of a bunch of examples. You can think of graphs, metric spaces, whatever you like. Okay, so now I want to tell you what's the structural Ramsey theorem. So then this notation over here will be in parallel to what I used for the classical Ramsey theorem. So now for any two structures AB, I can write B over A for, and now I will talk about embeddings from A to B. So I will be coloring embeddings. And this is more convenient than coloring substructures. And now, whenever I have three structures, A, B, and C, and some natural number R, then again, I have this arrow notation. So here, similarly as before, it is the shortcut for the following. So what I'm coloring? I'm coloring all embeddings of A in C into R many colors. And now, here I'm saying that I can find such a special F embedding from B to C, so that when I restrict my coloring to only those embeddings from A to C, which factor through F, yeah, so only those embeddings on the form where I take composition of F with some embedding from A to B, then this chi will be constant. This coloring will be constant on that set of embeddings.
Sorry, shouldn't A and B be switched in this chi and F? I presume that if you can embed A into B, then B should be larger, yes? And
yes,
you start with coloring of C over A and you ask for something monochromatic.
Yeah, so I color a composition. So first I go by embedding from A to B, and then I take my special embedding from B to C.
Okay.
So this is what
correct. Thank you.
Yes, it is okay, the composition. Okay, and now, so two things. I want to state what do I mean by structural Ramsey theorem. So I want to state what is a Ramsey class. So because for some structures it will be true, for some others it will not hold. But let me maybe first say that the classical Ramsey theorem we can phrase using this language as well. So it turns out that we can identify, so whenever we have, okay, maybe let me try to draw. So whenever we have, let's say n, yes, and whenever I have k, so before, okay, maybe I had m, I looked at k element subsets of m. Yes, so now instead of that, I can take linear order of size k, and I can take linear order of size m. And subsets, k element subsets of m, I can identify with embedding of k element linear orders, k element linear order into m element linear order. So I have identification between k element subsets of m and embeddings of k element linear order into m element linear order. So I can pass from one language to the other. And in fact, this is how I get restatement of the classical Ramsey theorem. Okay, so in terms of linear order. So now let me tell you what's a Ramsey class. And here, just to sort of wrap it up, I also want to, yes, I don't want this. Okay, so can I, okay, I can draw again. Again, what I'm doing here. So what does it mean to be a Ramsey class? Okay, so here is written everything up precisely, but here what I'm doing. So I'm coloring embeddings. Okay, let's cheat for a second, and let's think that instead of coloring embeddings, I will be coloring images of those embeddings, so isomorphic copies of those structures. So we think of the being Ramsey class in the following. So we have three structures. So first we have two structures. We have A, which is like a kind of a small structure. We have B, which is a middle-sized structure. A is embeddable into B. And now we also have some number of colors, R. And what we're doing here, what does it mean to be a Ramsey class? It means that we can find big structure C, kind of a solution. So let me draw it, a C. Yeah. Such that whenever I color, and let me think here, and identify embeddings with copies. So I color copies of A in C, all of them. So I color embeddings of A into C. into our many colors. Okay, so let's have some more things. Then I can always, no matter how I do it, I can always find a copy of B inside C. So here, let's say this will be my copy of B. Let me call it B0. So this is the embedding F that I had on one of the previous slides. So that all copies of A inside B0, they get the same color. Okay. And here is also a simple observation that I don't have to take arbitrary R. It's enough to take R equal to 2 to get equivalent definition because of induction. Okay, so this is what it means to be a Ramsey class. Hope makes sense. And yeah, so especially in like 70s and 80s, people got lots of results, lots of examples of Ramsey classes. And these are quite non-trivial results in combinatorics. So finite linear orders, this is the classical Ramsey theorem. But further, like people like Neshetril, Redel, and many others, yes, they got much more results. They proved that, for example, linearly ordered finite graphs, they form a Ramsey class. Yes, so like kind of Ramsey theorem holds for those structures. And here are some more examples, some important examples that I listed here. Linearly ordered finite triangle free graphs, linearly ordered metric spaces. So this one was, this is the latest result out of those that I listed. It's from 2007. And also there are posets. So here linear order extends the poset order. So this is a little bit different than previous examples where structure and linear order were completely independent. And also we have some results not only for relational structure, but for structures that involve functions. So here is some examples like finite vector spaces over some finite fixed field. They also form Ramsey class. And here are some non-examples as well.
Sorry, may I have a question? So looking at this list from the point of view, from the perspective of model theory, is there some reason to expect that for some of these classes the result would be easier and for some other would be more difficult, and for another would be non-true, would be false?
I mean, so there are some general methods like partite constructions, which are used to prove those kind of results. So they capture many examples. But if you just see some class for the first time, you don't know whether immediately if it is a Ramsey class or not. It's very often a non-trivial results. And also there are many very natural classes for which it is open if it's a Ramsey class.
Okay, so this is difficult, but is there some model theoretic reason for it? Like, for example, some theories are decidable in the sense of model theory. And
no,
I don't know.
These are all combinatorial reasons, I would say.
Okay, thank you.
Okay, so here's maybe like a quick sketch of the proof, because so not every class is a Ramsey class. When we take like all finite graphs, it's not. Like a very quick sketch of the proof on why it is not. So let me take as A. So this is my A. It looks like this. Here is my B. Okay, so this is a cycle. So this will be my B on 4 elements. And now it's easy to check that no matter how we linearly order B, so this was A, no matter how we linearly order these 4 elements, there is always a way to embed A into B so that the middle element is the largest in that linear order, and another way to embed A into B so that it is the smallest. Okay, so let me maybe say what I mean. So here, let's say I have 1, 2, 3, 4. So this is how I'm ordering my B. And I can always place M so that, yes, so the middle point is sort of the highest in my linear order. So this is how I do it. And same for achieving that placing A in a way that M is the smallest in the linear order. So this is a very simple observation. But now, if I try to find a solution, so okay, so I take a potential solution C, I take some graph, some big graph, and I linearly order this C. So a linear order, doesn't matter how. I just need some linear order on C. And now I do coloring of copies of A in C. And how do I do it? So, so color, okay, so here is this. So into two colors. So if I have a copy of A, so that middle point is the least, then I take color 0. If I take a copy of A such that middle point is the largest with respect to that linear order on C, then I take color 1. If it is middle, doesn't matter how I color. Okay, so if this one is the least, take color 0. If it's the largest, take color 1. And now, no matter, by the observation I just made, no matter how I place B as a copy inside C, I can always have both 0 and 1 on copies of A inside that B. Yes, so I have this B inside C, and I can always find a copy so that M is the biggest. It gets color 1. I can always have a copy of A in which M is the smallest. This gets color 0. So I cannot avoid any of the two colors. So it's not a Ramsey class. So there are many natural classes which are not Ramsey classes. Okay, so let's talk about structures a little bit more. I want to talk about amalgamation classes, about Fraı classes. So some observations, some small definitions. So whenever I have some structure M, I can look at all finite or finitely generated substructures. In case my language is relational, I can just look at finite substructures. And this is the age of M. So this is the collection of all finitely generated substructures. And now, whenever I have such an age, I can easily notice that it has what's called hereditary property. So it's closed undertaking substructures, and it has something which is called joint embedding property. So whenever I have two things in the H, I can find a third one, so that both here A and B embed into that third one. So yeah, so this simply follows from the definition of the H. Now I want to look at structures which have some additional properties, so that the H will also have an additional property, which we will call amalgamation. So what kind of structures I want to look at? I want to look at what's called ultra-homogeneous structures. So these are structures with the following, like quite strong property. So they have the property, so whenever we have finitely generated substructures, so here really, these are finite substructures. So whenever I have isomorphism between them, then I can always extend it to automorphism of the whole M. So let's think in the following. Let's just focus on maybe relational structures. So here I'm saying that whenever, so I have countable structure, and now whenever I have isomorphism between finite pieces of that structure, I can always extend it to automorphism of the whole countable structure. And the example you should keep in mind, the very first example, are rational numbers. Whenever we have some n natural number, whenever we have two n tuples, so there's only one isomorphism between them, then we can always extend it to order-preserving bijection of the whole set of rationals. Okay, so this is these are rationals. But there are lots of examples among other structures which have that property. Like for graphs, there is a famous Rado graph, which can be characterized up to isomorphism by the following property. So it's a countable graph, such that whenever we have two finite disjoint subsets of vertices of that Rado graph, let me call them A and B, so they are finite, then there is always some vertex, further vertex, V, inside the graph, so that every vertex in A is edge related to that V. However, no vertex from B is related to V. Yeah, so it's a very nice property. One can also characterize the Rado graph probabilistically. So start with a countable set. And now for any pair of points, toss a coin, let's say a fair coin. And if we get one, let's say if we get heads that we place an edge, if we get tails, we don't. And it turns out that with probability 1, what we get, it will be exactly the Rado graph. Okay. And now, if we look at H of an ultra-homogeneous structure, it will additionally have what we call amalgamation property. And I'm going to tell you in a second what it is. Okay, so how do we get ultra-homogeneous structures? We can build them from finite pieces. We can build them from Fraße classes. Okay, so I already mentioned hereditary property, joint embedding property. Yes, so H of any structure has those properties. And now we want additionally amalgamation property. Okay, so this is a property that let me maybe also draw a diagram. So here we're saying the following. So yes, we have two embeddings of A. We embed A into B and we embed A into C. Okay, so it's a little bit fixed, so maybe let's not draw names of the functions. So here we have F1 and F2. So these are our functions. And now we're saying that, okay, no matter how we pick those two embeddings, F1 and F2, we can always close the diagram. So we can always find some structure D and further two embeddings, G1 and G2, so that this diagram commutes. Yes, so that we have this one. Okay, so if we have those properties, then we have what's called Fraße class. And yes, it's a like classical result from model theory that whenever we have, okay, so because on one hand, whenever we take ultra-homogeneous structures, we get Fraße class. But on the other hand, the other way around. So whenever we start with a Fraße class, we can always find a limit. Limit will be an ultra-homogeneous structure whose H is the class that we started from. And moreover, there's unique such things. There's unique limit up to isomorphism. Okay. So going back to our earlier examples, yes, so we have these rationals with usual linear order. We have Rado graph. And it turns out that if we start from the collection, a family of all finite linear orders, then the limit of that class is the set of rationals with the usual order. If we start from the family of all finite graphs, then the limit is the Rado graph. Okay, and here let me mention the following result. It's not very hard, but maybe I will not have time to get into the proof. So here what I'm saying is that every Ramsey class is also amalgamation class. Yes, so we have amalgamation classes, Fraße classes. So we can produce ultra-homogeneous structures from them. So they have limits. And among those Fraße classes, we have like even nicer classes, which have this Ramsey property that I described, the Ramsey classes. Okay, so this is, these are those things. Yeah, so ultra-homogeneous structures, on one hand, they are very, very special. So in fact, people, yes, put a lot of effort to classify all ultra-homogeneous graphs, all ultra-homogeneous directed graphs. So especially for directed graphs, so this was work by Cherlin. So it's like a huge monograph on that. So people like really try to understand like, okay, so we have some kind of nice structures, ionometric spaces, graphs. We want to understand what are ultra-homogeneous structures among them. Yeah, this is also for the reason, because if we, like for me, like, okay, so I'm often interested in not just ultra-homogeneous structures, but on groups associated with them. So if we look at, okay, so I will talk about those groups right now. Okay, so I will define the groups associated to not only ultra-homogeneous structures, but to any, to all countable structures. So whenever we have some countable structures, anything, then we can look at the group of all automorphisms of that structure. Okay, so algebraically, yes, so what do we want? We want to preserve the structure. So if M is a graph, we want to make sure that we preserve the graph relation. So if 2 points are edge related, so this has to be if and only if their images are edge related. And this is really if and only if. It's not just a homomorphism where it goes one way. Okay, so we have to preserve the structure, of course. We have to be a bijection. So these are automorphisms. It's a group. We can compose such things. We have identity. But moreover, it's a topological group. So what's the topology? So let's think that M is equipped with discrete matrix. So it's a discrete space. So now, what does it mean to converge? So let's say Fn converges to F. So these are elements of oath M. If and only if for every x in M, yes, Fn of x converges to f of x. And as I said, on M I have discrete topology. So this last thing really means that from some point on, Fn of x will be equal to f of x. And of course, for different x's, we can have that happen at different points. Okay, so this is a topological group. So what topological groups means that operations are continuous. So operation of inverse is continuous, because what I did, I just put topology on my space. It's even it's not just topology; it's even a metric. So whenever, so okay, I can actually tell you what's the metric. So we can enumerate M. Doesn't matter how. We just fix some enumeration, and now we have some elements F and G, and we look at F of F and G, and we look at like F of 1, G of 1, F of 2, G of 2. At some point, they will differ. So we look at the first place where they differ. Let's say this is mth place, and now the distance we set is 1 over 2, 1 over 2 to m. Yes, so we have F and G. Okay, maybe I just wrote so D of F and G. So we look at 1 over 2 to m, where m is the least such that f of m is different to g of m. Yes, so I fix some enumeration of it. Okay, so this is metric. It's left invariant. We can easily turn it into a complete metric. There's like a trick to turn it into a complete metric. So in fact, this group is completely metrizable. It is also separable. It's what's called a Polish group. So this is exactly the definition. It's separable and completely metrizable. Okay, it's a topological group. So operations are continuous, inverse, multiplication. Okay, so we have lots of nice structure on oath M. We want to talk about those groups. There is a universal object among such groups, which is called often S infinity. And here, this is the group of all bijections of some countable set. So just I wrote natural numbers, but here I can put any countable set. So these are all bijections of whatever is your favorite countable set. And here I mean really all bijections, not just finitely supported. Okay, so this is like very first example of an old M. On M I don't put any structure. Okay, and here's some characterization of those groups. And like equivalence of 1 and 2 is quite nice, because here what I'm saying is that if I only look at automorphic groups of ultra-homogeneous structure, this is not loss of generality if we want to study automorphic group of countable structures. We can always, yes, by erasing original structure and adding orbits in various powers, we can turn our original structure into ultra-homogeneous one. And all these automorphic group of countable structures, these are exactly closed subgroups of S infinity that I just presented to you. And equivalently, these are exactly groups, and this is nice to have this topological characterization as well. So these are exactly groups that they have a neighborhood basis of the identity which consists of open subgroups. Okay, so we have those. All right, so a little bit of intro to dynamics. Yeah, so I'm collecting all pieces that I will need in a moment. So here's like a very nice, very strong property of a topological group. So maybe first, what does it mean to be a G flow or a flow if we know, if we have just G, which we fixed. So this is a continuous action of G, of our topological group G, on a compact Hausdorff space. So I will be only acting on compact Hausdorff spaces. Okay, so this is the G flow. And now definition, okay, it probably looks very strong if you only seen locally compact groups. So a topological group is extremely amenable if whenever we have a G flow, then it always has a fixed point. Okay, so in particular, every if you've seen amenable group, so every extremely amenable group is amenable. And interestingly, there is no extremely amenable groups among locally compact groups. So we have to go beyond. However, as we will see in a second, there are many extremely amenable groups among Polish groups, or even just among automorphic groups of countable structures. Okay, so let me drink some water. Yes.
I mean, I have a question. I mean, is this extreme amenability like related to some to one space, or is just the property of a group?
It's a property of a group.
Okay.
Yeah.
Sorry, just to be sure. So you take your G and then you consider all possible compact Hausdorff spaces X,
Yes.
and you demand that this for every such X, this whole G has a fixed point. So it means that for every small g belonging to capital G, G of X is equal to X, where this X was this fixed point, yes?
Yeah, so we have an action. It's continuous. Yes, so it continues on both variables. Yeah, so we have an action, and now yes, we being a fixed point exactly means what you're saying. It means that yes, so for every X is a fixed point. If for every G of X, yeah, so Gx here is equal to X. So G acts on X, and we're not moving the X anywhere.
Okay, thank you.
All right. Okay, so yeah, so here I will we can get lots of such groups using the work of Kwiatkowska that I'm getting to. But there were also before that there were not so many, but there were a few examples. Like there is like work by Gromov-Millman. So they proved that the group of all unitary operators on a separable Hilbert space has a much stronger property, which implies extreme amenability in particular. And methods were completely different. They used probabilistic methods.
I'm sorry, unitary groups on infinite dimensional separable, yes?
Infinite dimensional separable Hilbert space.
Okay, and what is this property? You mentioned that it is stronger than extreme amenability, yes?
Yes, some concentration of measure-related properties, which implies extreme amenability.
And sorry, just a silly question. Is it obvious, not using any fancy theorems, that at least one such group exists?
No,
Okay.
I don't. I mean, excluding one element group.
Yeah, of course.
Yeah, but no, this is all non-trivial. So actually, I want to. Yeah. So this was like in this context that I'm like Ramsey theory context. So the first example was really given by Pestov, and he showed that the automorphism group of Q is extremely amenable. And then, okay, so here is the theorem I was getting to. It was like hugely generalized by Kehris, Pestov, Todorchevich. And yeah, so here is what they proved. So we have a Fraă class, and we assume that there is this technical assumption that all structures in my Fraă class, they are rigid. So this rigidity or was already on some earlier slide, but let me say again. So this is like for linear order. So when we have our structure, it's rigid if the automorphism group is trivial. Okay, so like whenever we have some linear order on our structure, it satisfies this property.
Sorry, I don't recall if it was said already, but the group of automorphisms of Q with greater than are just all the order preserving bijections, yes?
Yes, yes.
Okay.
Precisely. Okay. Okay, so yes, so we have this setup. We have Fraă class. All structures are rigid, and then we take the limit, which we call M, and the following two things are equivalent. So the first one is that F, our Fraă class is a Ramsey class. Okay, so we have this combinatorial Ramsey theoretic property of the collection of finite objects. And this is equivalent to B, which is the automorphism group being extremely amenable.
And so this theorem of Kehris is assuming that M is countable?
Yes, so M will be countable.
Okay, so in this discussion, but this example about unitary operators, of course,
yes. So this is kind of like separate. Yes. So this is not in this framework. So these are earlier examples of groups which are extremely amenable.
Okay, thank you.
Okay, so this is very, very nice. It is if and only if. So now, if we want to get some extremely amenable groups, yes, among automorphic groups of accountable structures, we have to first turn our structures into an ultra-homogeneous structure. Okay, so that's not a problem. And then, so we have corresponding Fraă class, and so we can ask ourselves, so we have our Fraă class, is it a Ramsey class? Do we have this nice Ramsey theorem holding for F? And this is typically like extremely hard to decide, to see if something is a Ramsey class. Okay, so so my sort of goal is to give you some idea on what's going on here. So I would like to give you some idea on how, from being Ramsey, we get extreme amenability of the automorphism group. And I will focus on the example by Pestov. So we will be using the classical Ramsey theorem. So the sketch of the proof, it will be quite general, but I will focus on old Q specifically. Okay, so let's see some sketch. All right, so the very first observation is the following. So whenever I have a finite subset of Q, I can look at stabilizer of my finite subset of Q. So here I call it A. So this is the GA over here. And now I can look at the quotient space, G by GA, by the stabilizer, no problem. And I can also look at embeddings of A into Q. And I can identify those two spaces. How do I do it? So when I have G in G, and I have my A, so I can look at, and A sits specifically, it sits inside Q. I can look at G of A. Yes, so this is some copy of A inside Q. Yes, so now I can, and now whenever I have some other G, which is in the same coset, then the G of A will be the same thing. Yes, so I can identify. In fact, on this side I have the space of all cosets, and I identify that with copies. Yeah, so here embeddings and copies are the same because my structures are rigid. So copies of A in Q. Yeah, so this is how it works. So I have G, and I take for the G I take embedding, which places my A inside G of A. I mean, which takes my A to G of A. Yeah, so here sort of I think that my A lives internally inside Q, but here I see it sort of external. Yes, so I take my A to G of A. So this is the embedding. This is the copy of A. I associate to G, and if I replace G by something else in my coset, I will get the same copy of A in Q. Okay, so this is the identification I will be using all the time. Okay, yeah, it disappeared now when I went to another side. Okay, so now let's see the following. So here what I'm saying, so I have some natural number P, I have some function which goes from G to some power of real numbers, some finite power. And let's assume that it's left uniformly continuous. Okay, so I just told you what could be a metric on G, like some slides before. G is an automorphous group. So that metric is in fact left invariant. So when I say left uniformly continuous, you can think that the uniform continuity with respect to that metric, if you like. And it's also bounded. My function is bounded. I also have a finite set T, and I also have some epsilon. And now what I'm saying, so okay, so if we look at like values of F on elements of T, okay, they can be very far away from each other. But it turns out that, okay, so I can shift T so that like all shifted values of T are very, very close. They are within epsilon. Yeah, so that's what I'm saying here in this last line. Okay, so what do we do? So we have our F and we want to replace it by F bar, which is nicer, which has finite range. And we can do it because, okay, so this left uniform continuity in fact give us that when we look at, here, we look at here, this is what I wanted. Yeah, so we can take such a big A by left, so having epsilon, so here epsilon over 2, we can find a huge A, some A, large enough, so that F is constant up to whatever I wish, so epsilon over 2, on that coset space. So that's one thing. Another simplification I want is that, so okay, so now I have like on the cosets, like values are very, very close, they're up to epsilon, so let's make another estimate simplification that that I need. So it will be that I replace my f by f bar with finite range. So so like for any coset, I pick like one of the values that I achieve on that coset, and this will be my f bar. Okay, so I replace my original f by some f bar such that it has finite range and it is constant on cosets. Okay, so now, yeah, by this identification that I mentioned at the very beginning, I can think of my f bar as, so first as a coloring of cosets into k many colors. So k is some possibly big natural number, and this is in fact coloring of copies of A in Q into k many colors. Okay, so I started with some f, and I turn it into coloring of copies of A in Q into k many colors. All right, so now we want to use Ramsey in a second. So on one hand, I'm taking S, where I collect all the relevant copies of A. So relevant means that they come from some T. Okay, so for every T, I have such a coset. This coset is identified with some copy of A inside Q. Okay, and I have all these copies of A that correspond to elements of T, and I take some S, which contains all of them, a finite S. Okay, so now the next thing I want a copy of S, S0, such that F bar, so F bar, okay, is this now coloring of copies of A in Q. Now using Ramsey theorem, like classical Ramsey theorem, I can find S0. No, sorry, I have this. Okay, I have this A, my small structure. I have this S, middle-sized structure, and now using the Ramsey theorem, I can find some big structure, which without also generality, I can think that it lives in Q. So in fact, I can color the whole Q so that it is monochromatic. Okay, so like summarizing what I'm getting S0, a copy of S inside Q, such that all copies of A inside S0, they get the same color. Okay, S and S0 are isomorphic. So I can find some G which takes S to S0. And now, okay, so what do I have? Like for S0, I have that the following. So yes, so we are monochromatic on S0, and we pushed by G S to S0. So what we're really getting is that F bar is constant on that shifted T. So here, this is what we're saying. Okay, so if we come back to our original F, so we will get that those two values are equal up to epsilon. Okay, so this is end of the proof of the proposition. Here I'm repeating the proposition. Okay, and there are some more steps, like kind of sort of standard steps. Okay, so here we already used Ramsey theorem. So what are those other things that we have to say? So okay, so now we have our flow. Yes, we have some flow. We want to show that it has a fixed point, and we're looking at this kind of sets like over here. So phi is some uniformly continuous function here from X, not from G, and epsilon is something positive. T is some finite subset of G. And we look at all these x's in X such that no matter what T we pick in our finite set, like P of X and P of this translate of X, they are very close. They are within epsilon. So this set is closed. And in fact, all those sets, they have finite intersection properties. So whenever we take finitely many of those, their intersection will be non-trivial. By compactness of G, there is some X, which is in the intersection of all of them. And we claim that it's a fixed point. And suppose it's not, then we can find some G, which shifts away X from X, yes. So now for that G, we pick some uniformly continuous function phi, which assumes 0 at X and 1 at the other point at Gx. And just by the definition of these sets A, phi, epsilon, t. So if we take this phi, if we take epsilon equal to half, and if we take just singleton of G, so this is an element from the group G, we see that our X is not in that set. And okay, so this gives a contradiction. Okay, so this is how things works here. And yeah, so there are many more things that one could say here. So I thought that maybe I will just very, very briefly tell you what one can do next with those things. So one can talk about using this extreme amenability, one can describe universal minimal flow. So this is a continuation of what Kwiatkowska did, and then other people continued their work. So what's the universal minimal flow? So it's a flow which is minimal. So minimal simply means that all orbits are dense, and it's universal. So it's kind of largest, but largest here in the surjective sense. So it's largest in the sense that okay. So this is what I want to tell you what it is. So now here I'm saying okay. So here I have M of G. And here I have also another flow. Yes.
So what is this M of G? Is this?
So this is space
X?
on which I'm acting. So this is usually how we denote it. So before I had X, like G was acting on X. So this was the space on which I'm acting.
Provided that this action is minimal, yes?
Yes, action is minimal, exactly. So this action of G on M of G is minimal. So that's one thing. Another thing is that whenever I have some other minimal flow, so this is another minimal flow, then I can always find, let me maybe draw it here, the phase space X. I can always find some surjection, continuous surjection, pi, which commutes with G, yes? So commutes with G simply means that I have pi of Gx equal to G of pi x, yes. Yeah, so this is what it means to be universal minimal flow. It's a simple observation that G is extremely amenable if and only if universal minimal flow is a single point. Such a thing always exists and is unique up to isomorphism. It's a result from 60s. And again, like interestingly, like locally compact groups, they don't behave nicely here. In particular, their universal minimal flows are non-metrizable. They are huge. They embed checkstone compactifications, which in particular have size 2 to continuum.
Sorry, M of G embeds, meaning that you can embed checkstone compactification into
Yes,
M of G. Okay.
Exactly. Okay. Yeah. However, many of the automorphist groups, they behave nicely with regard to universal minimal flows. Okay, so there can be extremely amenable, like for example, okay, so I mentioned at the very beginning that when we have linearly ordered graphs, finite linear order graphs, and here the graph relation and the linear order relation are completely independent from each other. Then this group is a Ramsey class, so from the Kwiatkowska result. the automorphism group of the corresponding limit, so like a linear ordered Rado graph, that automorphism group is extremely amenable. Okay, so, but okay, let's say we want to look at not at linearly ordered graphs, we want to look at the Rado graph. Okay, so we want to look at automorphism group of the Rado graph. So I told you what the Rado graph is. I told you that it's not a Ramsey class, like the class of all finite graphs, it's not Ramsey. So the automorphism group of the Rado graph is not extremely amenable. Okay, but still it turns out that the universal minimal flow of the automorphism group of the Rado graph, it's nice. It's kind of very tame. It's metrizable in particular. And here I'm going to tell you what it is. And this will be kind of like a special case, sort of canonical example of which illustrates what further Kekris, Perstov, and Todorczewicz did. So okay, so let me carefully explain what it is, and I guess I will finish with this example. All right, so once again, so we have automorphism group of the Rado graph. We want to understand the universal minimal flow. So it's an ultra-homogeneous structure. It's a Frasse limit of the class of all finite graphs. Okay, so this is one object. Another object are like it's a linearly ordered Rado graph. Let's call it this way. So okay, so here we have not just F, we have linearly ordered graphs, linearly ordered finite graphs. This is also a Frasse class. It has Frasse limit. Let me denote it by this R less than over here. And okay, so we know that automorphism group. Yeah, so again, disappeared something. Automorphism group of R less than is extremely amenable. But we want to understand this one, what we can say about the universal minimal flow of this one. So here the universal minimal flow is a single point, and what's going on with O there. Okay, so so the very first thing one shows is the following. So when I look at the Frasse limit of this space, this R less than, and I forget the linear order part, what I get the Rado graph. So this is what we have. And now I'm looking at the following space. So I'm looking at all possible linear orders on R. Okay, so I have my countable graph, and I can linearly order it in many, many ways. I take all possible linear orders, and I have this LO of R, and this is not just as a set. It is a nice compact space. And how can we see it as a nice compact space? Okay, so we can code it as follows. Yes, so let me take like one linear order. Okay, so I have some linear order. So on R. And now I can, okay, so for any two elements, A and B in R, okay, so sometimes I have A less than B, sometimes I have B less than A, sometimes they are equal. So let's say, how do I code this information that A is less than B? So I can, so for pair AB, to pair AB, I can associate number 0 or 1. Yes, so I can associate to this, let's say number 1. So if I have A less than B, to this pair, I associate number 1. In all our other situations, so if B is less than A, or if B is equal to A, I associate to pair AB, and it's an ordered pair, 0. So if A is B is less than A, or if B is equal to A, then this pair gets labeled 0. Okay, and this is how I code my linear order. Yes, so to any pair of elements in R, I associate 0 or 1. Okay, and now if you look at this space a little bit more carefully, you will notice that it's a Cantor space. Yes, so this is here I have some countable set R times R, it's just a countable set. And here I have, yes, 2-element discrete space. So it's a Cantor space, like 2 to, I don't know, 2 to n, maybe you've seen it written like this, or 2 to omega. Okay, so I see LO of R as, in fact, a closed subset of a Cantor space. So it's a compact space. So I just gave it a compact topology. And it's not just a space, it's a G-flow. Yes, so what do? So I take some, again, element in L of R, and I take some G. Yes, so I want to understand what is this one. Yes, what is this order? So I take 2 elements, X and Y, in R, and I say that X is less than Y with respect to this order that I'm obtaining now, if and only if inverses of X and Y, yes, so inverse of X is less than inverse of Y with respect to this original ordering, yes? So I'm basically shifting X and Y, and I'm saying that X is less than Y with respect to new order, if and only if G inverse of X is less than G inverse of Y with respect to old order. Okay, so now I have a G-flow, and it turns out that this is the universal angular flow of the automorphism group of the Rado graph. Okay, so this is like okay, so this is like a bunch of results they proved. So I will essentially stop here. So there were like later results by other people where they showed by when universal minimal flow is metrizable. So then one has to look at what's called Ramsey degrees. Then like another group of people, they described how metrizable universal minimal flows, not just for automorphic groups, but for Polish groups, how do they look like? Yeah, so, and there were many more developments, like especially in Ramsey theory. So this correspondence also pushed many new developments in Ramsey theory. So people discovered many new Ramsey classes because of that. Okay, so let me maybe stop here.
Thank you very much. Okay, any questions or comments?
And just a very basic question concerning terminology. I presume that the terminology is such that if something is extremely amenable, then it is amenable, but somehow I have doubts about amenability of this unitary group on separable space. So I'm confused.
Okay, so amenable. So okay, so one way to define. I mean, yes, it is amenable. So, but we don't look at it as a discrete group, as a topological group. So it also amenability makes sense. So, yeah, for example, you can consider actions of groups on compact spaces, and if there is invariant probability measure, no matter how you pick the flow, then this group is amenable.
So the answer is positive.
Okay, so you can. So I mean, just don't look at topological groups as discrete groups. Then yes. But it's not
okay.
true, I think.
Okay, any other questions or comments? Any questions or comments from people on Zoom? Okay, if not, let's thank Ola again.
And also, I don't know if I'm still connected.
Yeah.
Okay.
Yeah.
So we before you all disappear, let's thank organizers for doing this extremely nice workshop. So there are like all the people here and students who are involved in the organization as well.
No, this is stop share, but I don't see stop recording here.
Okay, just give us a second. We have to stop the recording because it's